Let's consider a simple three-link mechanism like that, where you have one link with length 1 and a second link with length 2, and then a third link which has length 0 but has a claw attached to it, so the robot can actually grasp something. Now we introduce some angles here, so let this be theta 1 and let this be theta 2, and now the angle of the claw is gonna be theta 3. We can now write down the transformation matrix from the base to the wrist using the Dennevit-Hartenberg convention. And so we have cosine of theta 1 plus theta 2 plus theta 3 minus sine of theta 1 plus theta 2 plus theta 3. Then here the same, and here the cosine. So that's the rotation matrix part of the transformation matrix. And now we write down the equations for the translations, which are L1C1 plus L2C12 up. And we have here L1 S1 plus L2 sine of theta 1 and theta 2. So there's a 0 here and a 1 here to make the matrix complete. So the inverse kinematics problem is now solving equations that give us the position of x and y as a function of theta 1 and theta 2. The question is, how do we do that for the rotation? One way of doing it is actually thinking about a simple representation of the problem that we have. And what we could do is we could say this point here on the anti-vector has an x-coordinate, a y-coordinate, and an angle phi. And so when we do that, we don't care at all about all the kinematics in between. Could be anything, could be an arm that has multiple joints, multiple links, whatever. And we could write down something like a transformation matrix that looks like that. It would be cosine of phi minus sine of phi, sine of phi, cosine of phi, and then 0, 0, 0, 0, 0, 1, 0, 0, and there would be x here and y here, 0 and 1. So now it becomes pretty clear. If you want to solve the inverse kinematics, we have just to equate things like x with the entries of this matrix, or y with that entry, and of course cosine of phi is the same as cosine of theta 1 plus theta 2 plus theta 3. So we can actually write that down and say, let's get rid of this real quick. We can write down cosine of phi is cosine of theta 1 plus theta 2 plus theta 3. Similarly, sine of phi is where is the entry here? Sine of theta 1 plus theta 2 plus theta 3. And we can write down x equals L1 times cosine 1 plus L2 times sine. That's actually the cosine of theta 1 plus theta 2, and for y it's L1 times sine of 1 plus L2 sine of theta 1 is theta 2. So our goal now is to solve those equations for theta 1 and theta 2 and theta 3, and to get x, y, and phi, which are the desired pose parameters, on the right hand side. So let's recap real quick. We have x equals L1 times C1 plus L2 times C12. We have y equals L1 times S1 plus L2 times C1 S12, and we have cosine of phi is 1, 2, 3. Sine of phi is sine of 1, 2, 3. So now we can use the following identities. Obviously we have to break cosine theta 1 times cosine of theta 2 and sine theta 1 times sine of theta 2 apart. And so we can take advantage of some common trigonometric identities. So once, if you have something like cosine of something times cosine of something else, it's the same as writing down cosine of 1 times cosine of 2 minus recap real quick these equations. We have x is L1 times cosine of theta 1 plus L2 cosine of theta 1 plus theta 2. Y is L1 sine 1 plus L2 times sine of theta 1 plus theta 2. So what we want to do is we want to solve these equations for theta 1 and theta 2. How are we going to do that? So there's a nice trigonometric equality which says that the cosine of two angles added together is just the cosine of them multiplied minus the sine of them multiplied. Similarly, we can say that if we have the sine of two angles that are added together, it's just the cosine of one angle times the sine of the other angle plus the sine of the first angle times the cosine of the other angle. So now what we can do is we can use these inequality or equalities to put them into the x expressions for x and y, and we can look at equation like that where we square them and fill everything in and solve it, and it will get us something like this: L times L2 square. So L1 L2 times cosine of 2. So we have now an expression that only has a cosine of theta 2 in it, and we have all the other parameters known. So we know x, we know y, we know the length, of course. And the key here is now you can solve for cosine of theta 2, which is x plus y squared minus L1 squared minus L2 squared, and we divide this by L1, L2. So now how to solve this is not the problem, but the key is really what to do next. And one naive way of doing it would be to say, well, we have cosine of theta 2 here, we can just take the arcus cosine of the right hand side and we'll be done. The problem with that is that there are many possible solutions, and if we would do that, we would limit ourselves to having only two solutions, because the cosine looks somehow like this. So it's symmetric, so if you have this value, it can be either here, it can be here, and of course it can be in all the other quadrants as well. How to get there? Well, one way of thinking about it is to say, well, sine square of something plus cosine square of something is actually 1. So you can find an expression like this. You can say the sine is plus minus 1 minus the cosine of the same thing. So if you do that, we can actually rewrite the expression here into an expression that is dependent on sine. And now what we can do is we can say, instead of using the arcus tangent, the inverse cosine, we can use the arcus tangens. And so what we can do is we can say something theta 2 is a tan 2 of sine 2 divided by cosine 2. So the arcus tangens 2 is actually giving not only values back between minus pi and plus pi, but actually from minus 2 pi to the other way around. So instead of just getting values from in these two quadrants, you actually also get values in these two quadrants. And that's of course what we need in order to get all the possible 4 solutions, if there were so many. And now we have, of course, here an expression. Once we have a plus sign and then we have a minus sign, and this gives us already 2 different solutions that we can solve the arcus tangens for. You can now use similar tricks to find an expression for theta 1, and then of course find theta 3 from the equations that involve both theta 1 and theta 2, such as cosine theta 1, theta 2, theta 3.